Alright, we are doing special right triangles today, and I decided to combine two sections into one to give you less videos to watch. So this is from 9.6 and 9.7. By themselves, this would be a really short video if I just did one. So let's just get through this one, and your objectives are: you will be able to identify the ratio of side lengths in a 30, 60, 90 triangle. You will be able to identify the ratio of side lengths in a 45, 45, 90 triangle. And you will be able to identify a Pythagorean triple. Sounds like fun, huh? Alright, so we've got two theorems. Yay, I know you're excited. Okay, so we've got Theorem 72, which states that in a triangle whose angles have the measure 30, 60, and 90, the lengths of the sides opposite those angles can be represented by x, x root 3, and 2x. So let's draw the angles in. 30, 60, 90. Okay, so opposite the smallest angle is going to be the smallest side, which in this case is x, followed by x root 3 opposite the 60 and 2x opposite the 90. You can shorten this theorem and just call it the 30, 60, 90 triangle theorem. This is one type of special triangle.
Well, isn't that special?
Yes, yes, church lady, it's special. That's why I called it a special triangle. Moving right along. Theorem 73 states that in a triangle whose angles have measures of 45, 45, and 90, the lengths of the sides opposite these angles can be represented by x, x, and x root 2 respectively. Okay, so we can draw the angles in 45, 45, 90. Now a couple of things here. Notice that the two base angles, if you want to call them that, have the same measure, which means that this is also an isosceles triangle, which means that this side and that side are congruent. And oh, look at this. That side's measurement is x, and so is that side. It's funny how that works, which leaves x root 2, the biggest side, opposite your right angle. And we can call this the 45, 40, 90 triangle theorem. Again, another type of special triangle.
Well, isn't that special?
Yes, and I would appreciate it if you stopped interrupting me, church lady. Alright, so let's put it into practice. We have this. We know this type. It is a hypotenuse of 2x. Why do we know that? Because this is a 30, 60, 90. How do I know that? Because I only see a 60. Well, if this is 90 and this is 60, that only leaves that can be 30. Let's see what they want us to find. BC and AC. So since it's a 30, 60, 90, we can place x, x root 3, and 2x on the diagram. Now remember where they go. Okay, right there. Opposite the smallest angle is the smallest side length, x, same, and we go up. Now, here we've got 2x equals 10, and since 2x equals 10, we can then figure out that x equals 5. Because if we have 2x equals 10, divide both sides by 2, you get x equals 5. Then you just substitute that 5 into the other sides. Well, if x equals 5, then BC must also be 5, because it's not 2x, it's just x. And then the other side would be 5 root 3. Simple enough. So 5 and 5 root 3. Okay? Simple, simple stuff. So let's go on to special triangles based on side measurements. So there are families, notice I put quotes around them, of right triangles called Pythagorean triples. These are right triangles whose sides are made up of whole numbers that satisfy the equation a squared plus b squared equals c squared. Okay, few of them are 3, 4, and 5. Now what do I mean by they satisfy that? Well, so I've got these three side measurements. If I plug these in, 3 squared is 9, 4 squared is 16. If you add those two together, I get 25, and the square root of 25 is 5. So basically, when you square these numbers, they are all perfect squares. Okay, and they all come out perfectly. Alright, so we've got 3, 4, 5, 5, 12, and 13, 7, 24, and 25, and 8, 15, and 17. Those are the ones that you're going to see most commonly. And if you don't recognize them, that's fine. You can still use a squared plus b squared plus c, equals c squared define some of this stuff. This is just a way to make it easier, though. If you don't get it, it's not a big deal. It's just, like I said, it's kind of a shortcut. So, little game. Oh no, the families have been separated. Okay, these are the parent Pythagorean triples that I told you about. 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17. All right, so these sets of sides all belong to one of those 4 families. What I'd like you to do is pause the video, see if you can put them with the families they belong to, and then when you're done, unpause me and I'll put them in order for you. So go ahead. Now would be a good time to pause. And if you did what you were supposed to and paused it, then this doesn't sound weird. If, however, you didn't listen and you just kept watching the video without pausing it, then that probably sounded a little awkward. But anyway, moving right along, I digress. So we've got all these mixed up. Let's put them in the right order. Watch this. Yeah, like my sound effects? They do get better, I promise you. All right, so let's see how these all fit into where they are. So I've got 6, 8, and 10. Well, how in the heck is that? Oh, look at this. 3 times 2 is 6. 4 times 2 is 8. 5 times 2 is 10. If you multiply them all by the same thing, then it is part of that family. So you can either multiply or divide by the same thing, and it will be part of that family. Like here, I multiplied by radical 3. So 3 radical 3, 4 radical 3, 5 radical 3. Here, I multiplied everything by 5. Okay, and it works over here too. Look, 5 times 2 is 10, 12 times 2 is 24, 13 times 2 is 26. But wait a minute, what did I do here? I divided by 2. 5 divided by 2 is 2.5, 12 divided by 2 is 6, and 13 divided by 2, 6.5. Okay, this one, a little more confusing. I wanted to throw you off. Yes, I wanted to. Okay, because here's the thing. I've got a 7 and a 25. So if you can figure out how I got 12 root 2 from 24, then you can show that that's part of the family. Thing to look at here is, what do these two have in common? This part right here. Root 2 over 2. So how come instead of 24 root 2 over 2, I have 12 root 2? Well, that's simple. If I do 24 radical 2 over 2, this reduces. 24 divided by 2, you can reduce that so that it's just 12 radical 2. So a little kind of spiral learning there for you to go back to radicals in case you had struggled with that on the last quiz. So yes, that's part of that. And then here, obviously, I just multiplied by 2. Here, multiplied everything by 3. And then, well, what did I do here? Well, the easiest thing to do here would be, okay, well, let's look at the middle number, since it's the only whole number. How did I get from 15 to 5? Well, 15 divided by 3 equals 5. So if you did 8 divided by 3, you would see that it's 2.6 repeating. And if I did 17 divided by 3, you would see that it's 17, or 7. That's not right. It should be 5. At any rate, at least I caught my mistake. Okay, so just an example of some of the families for you. This was a real easy video overall. Let's try something a little bit harder though. Okay, given that we have a square with a perimeter of 28 root 2, find the length of the diagonal. Now, I'm not giving you a diagram in this. Time for you to do some work and figure it out. So what do we know about a square? We know that it has 4 equal sides. So since it has 4 equal sides and its perimeter is 28 root 2, take that, divide it by 4, and that gives you that each side is 7 root 2. So what type of triangle will the diagonal create? Well, think about it. If you have a square and you have the diagonal, remember the diagonal of a square bisects the angle. So if this whole part is 90, each one of these has to be 45. So it's a 45, 45, 90 triangle. Okay, so what does that tell us? Well, it tells us that the sides have a ratio of x, x, and x root 2. So the diagonal would be your x root 2. And since we know that x, which is the length, is 7 root 2, we can just plug that in, 4x, to find the length of the hypotenuse, or in this case, diagonal. So we do 7 root 2 times root 2. And remember, when you have square root of something times itself, you basically just get rid of the radical. So 7 times 2, that's how I got that, equals 14. All right, so that's about as hard as problem as you're going to get from this particular section on a test. All right, so that's a wrap. Almost. Don't stop the video yet. This is all leading up to trig functions, which is going to be your next lesson, and it's going to be a little...
Well, isn't that special?
Would you stop interrupting me? Okay, it makes more sense to combine that lesson into one also, so I'm going to leave you with this problem, and then you're going to have the next video for tomorrow. So given this triangle, could you determine the measure of angle A, the measure of the hypotenuse, and what other information could you find? I want you to bring that into class tomorrow so I can take a look at it. Okay? Oh. Yes, to be continued. Yes, it's dorky music. Hope you're ready for tomorrow's video. Have a good night, day, whatever it is by you.